Linear relations, linear equations, y equals mx plus b. While there are several ways to write a linear equation, the most important is called slope-intercept form. And that's y equals mx plus b. The parts of the name show up in the equation. The slope is is m, and the y value of the y-intercept is b. In other words, the point 0b is on the graph of the line, and that's on the y-axis because the x value is 0, which means it has to be on the y-axis. M and b can be any two real numbers, and I'm not going to talk about what a real number is right now, but it's any number you can think of, like even pi or -1/2 or square root 2. We're going to return to example 1 from our last video. We had found that the growth factor of the tile pattern, well, just as a refresher, we can see that those two tiles are added from figure 0 to figure 1, and then those two tiles are added from figure 1 to figure 2. So the growth factor was 2. In terms of an equation, that will represent the tile, the pattern. This becomes that's our slope, m. So it's our growth factor, but the growth factor is the slope. The b value in the equation is determined by the number of tiles in figure 0. So if we put these two parts together, the equation, which represents the tile pattern in example 1, is y equals, and I guess I didn't I point out that the number of tiles in figure 0 is 3 there. So here we have our slope, m is 2, so y equals 2 times x plus 3. It grows by 2, and it starts in figure 0 with 3 tiles. We can also, and so let me write that over here in our example. So we have y is equal to 2x plus 3. And in function notation, so we can use our shortcut notation. Remember last video we used this shortcut notation. So it was f of a number, and here we're going to do f of x because it's just the general situation where we don't know what number we're talking about, which figure number, but it equals 2 times x plus 3. And written this way, it is called function notation, and I said that by accident just a moment ago. We can use the equation to verify the number of tiles in figure 0. So when we write it this way, this says that the number of tiles in figure 0 is equal to something. And so here's what we can do. We do 2, and then I'm going to highlight this figure 0 right here. So we're talking, that's our input. So 0 becomes our input in this situation. So it's 2 times 0 plus 3. Well, 2 times 0 is 0. So that means that we have 0 plus 3, which is 3. So this says that there are 3 tiles in figure 0. And sure enough, there are. And when we do this, it makes it clear why we always start a tile pattern with figure 0. Remember I had said we have to start with figure 0. We don't start with figure 1. And that's because if we plugged 1 into the equation, so here we have, here we have a 1 that we're plugging in. So we have a 2 times 1, and then plus 3. 2 times 1, that is 2 plus 3. and 2 plus 3 is 5. This says that there are 5 tiles in figure 1. And if we look up here, sure enough, in figure 1, there are 5 tiles. So it works, which is good news. All right. It's also helpful if we need to predict the number of tiles in some specific figure number, like let's say figure 10. So this says, hey, how many tiles are in figure 10? Well, again, we just plug in. We say 2 times 10 plus 3. Well, 2 times 10 is 20, plus 3 is 23. There are 23 tiles in figure 10. Let me just highlight this so that you can remember where that 10 comes from. Conversely, it's also nice for finding which figure number has some specific number of tiles, say 74. So this right here says which figure number, x, we don't know it, it's an unknown, which figure number has 74 tiles? So the way that we can do this is, if we look up at our original up here, f of x is equal to 2x plus 3. Well, what we're doing is we're saying, hey, I know that f of x, right there, I know that equals 74. So it's going to be, that's what this says, equals 74. So we're going to take the 74, we're going to put it right there. So we'll have 74 is equal to the 2x plus 3. And now we can solve that equation by isolating the x. So we subtract 3 from both sides, and we get, well, this was not a good example at all. It should have been 75. And the reason why I know that is because I'm going to get an odd number here, which is not divisible by 2. So we're going to, on the fly here, we are going to change this to 75. And I'm going to change this to 75. And I'm sorry you're going to have to do this in your notes, but it's good to see how things happen sometimes. That's 72 is equal to 2x. Now we can divide by 2, and we get x, which is the figure number, is equal to 36, because 72 divided by 2 is 36. So the figure number 36 has 75 tiles, so make sure to change it over here as well, 75. All right, while it's unconventional to write an equation like y equals 10 minus 4x, it is still considered to be in slope-intercept form. Sorry for the jump there, I had to sneeze. So this is in slope-intercept form. All right, now we're going to find the equation for this tile pattern below, and it says, be careful, there is a trick. All right, so one thing we can see is that as we move from this figure to that figure, we can see that it's increasing by these 3. And as we move from that figure to that figure, we can see that it's increasing by 3. So that means our slope, m, is 3. And now we just need to figure out our b value, which is our the number of tiles in figure 0. But wait a second. We don't have figure 0. So that means we need to move backward and find figure 0 and see, well, what would figure 0 look like? Well, if we're adding 3 tiles when we go this way, we are adding 3, adding 3. Then when we go that way, we need to subtract 3. So we're going to take these 3 tiles off and just be left with those 2 tiles right there. And so that means that there are 2 tiles in figure 0. So our equation in function notation will be f of x is equal to the slope is 3, that's the growth factor, 3x, and then plus 2. And that is linear relations, linear equations, y equals mx plus b, the slope-intercept form of linear equations.